lecture number 38 and 39. Let us revise last time what we have done. We have seen a basic differential amplifier, a dual input balance output differential amplifier. And this is what we have arrived at. We have arrived at its DC transfer characteristics. And we have commented that if the difference between the two inputs, V1 and V2, which is VD, differential input, if the difference between the two input is very, very small, only then both the transistors will be on and it will be working in the linear region. So this is the linear region of the characteristics. And if the difference between the both the inputs increases, one of the transistors will, having one of the transistors will be fully on while the other will be off. That's what we have seen over here. So if the difference is positive, then your M1 transistor will be fully on and M2 transistor will cut off. So that means beyond this yellow color linear region, this MOSFET differential amplifier will not work as a differential amplifier. So only within the linear range, it will work as a DFAM. That is what we learned from this DC transfer characteristics. All right. So the question is, why do we go for such a MOSFET differential amplifier? See, the maximum differential input signal for the MOSFET differential amplifier is much, much larger than the BJT differential amplifier. All right. And the second reason is that the gain of MOSFET differential amplifier is much smaller than the gain of BJT differential amplifier. And many DFAMs are constructed using MOSFETs because it is possible to provide high input impedance, which will help the amplifier avoiding loading of the source, which is important in case of op-amps or instrumentation amplifier. All right. Whereas a MOSFET differential amplifier cannot provide a high gain because it avoids the loading of the source. All right. And a MOSFET can be easily fabricated in the integrated circuit form. Okay. So these are the possible reasons, in which we go for a MOSFET differential amplifier. So let's start with today's analysis. As we have said, the DC analysis of MOSFET differential amplifier, the good news is that it's same for all four types of DFAM. Which are the four types of DFAM? DIBO, dual input balanced output; DIUO, dual input unbalanced output; SIBO, single input balanced output; and SIUO, single input unbalanced output. And for AC analysis, we will be dividing into two parts. SIBO and DIBO will be deriving AV, ACM, and CMRR. That's almost like a every time question for examiner. Derive the expression for differential gain, common mode gain, and CMRR for any of the differential amplifier possibles. All right. So we'll go today through the DC analysis and then AC analysis. So let us start with lecture number 38 and 39. So you all can draw along with me. So we will start with the DC analysis first, and then we'll go on with the AC analysis of the same. So you can draw along with me the basic DIBO differential amplifier. So let us start. Basic dual input, balance output, DFAM. I'll be writing the short form now. Instead of differential amplifier, I'll write DFAM. Okay, so let's draw this differential amplifier, a unique differential amplifier. So it goes like this. We have two N-channel MOSFETs. Okay, connected in such a fashion. The drain terminal, we have drain resistance, and both the drain resistance are tied together to VDD supply. This we can call it as RD1. This is RD2. Then both the inputs, we can have an internal resistance as a source, but I'm skipping it over right now for simplicity. So here we have input AC input number one. We are calling it V1. So this is, mind you, this is AC input. Okay, this is AC. And the second input is over here. You can draw along with me. Okay, and we have seen how the two inputs can be differential. They can be of the same magnitude but out of phase, right? Like this. Okay, they are out of phase signals. Let me draw. So both the source terminals are tied together to a common resistor, which we call it RS, and it goes to a negative supply minus VSS. Okay, so I hope it is visible now. And where do we take the outputs? Outputs are taken across here. these terminals. This is VO1, this is VO2, and the difference between them over here, plus minus, it is V out. All right. Completed so far, whatever we have done over here? Yes or no? Hello, students.
Yes, sir.
All right, great. And because of this MOSFET being on, this is M1 and this is M2. The current flows through the circuit, which is ID1 and ID2. And this is same as IS1 and IS2. So basically in a MOSFET, we have seen that the drain current is approximately equal to the source current. So ID1 will be equal to IS1 and ID2 will be equal to IS2. And that will be equal to the total current flowing through this resistor, RS. All right. Now we have to assume certain things. So write down assumption. Number one, we assume that both the transistors are matched. So M1 and M2 are matched. What do you mean by matched? Their threshold voltage is same. So VTO1 is equal to VTO2 is equal to VTO. And the transconductance is same. KN1 device gain is same. KN1 is equal to KN2 is equal to KN. That is what you mean by matched. And secondly, the resistors RD1 and RD2 are similar. So resistor RD1 is equal to RD2 is equal to RD. All right. So let's go with DC analysis. So what we have for DC analysis, let's write it down over here. First, we go for DC analysis. So tell me, what do we do in DC analysis? We remove all the, acha, let me tell you what is AC again over here. This is AC and the output is AC, this over here. And this is DC. Okay. This is AC. All right. So what is the first condition for DC analysis? The first condition is remove all AC sources. Means make them zero. So make V1 equal to V2 equal to zero. All right. So can we draw that now over here? Yes or no? So let's draw it. So this is connected to zero. So this will be grounded. Rest everything will be as it is. All right. Now I'm doing one more thing. This is RD. This is RD because both the resistors will be same. This will be VDD. Okay. Here also it will be VDD. Actually both are same. And here, see this. Now this one single resistor RS, can I split up into two resistance? Can I split up this RS into two resistance? Yes or no? Yes. How? If I make RS parallel to 2RS, 2RS parallel to 2RS, what I will get? Equivalent RS only. Do you agree? So here also I'm doing the same thing. Here also what I'm doing is I'm just splitting this into two parts. This will be 2RS. This also will be 2RS. Okay. And this is connected to negative supply, VSS. Got it? So this is your DC equivalent circuit which we get. Now, do you see this 2RS and this 2RS is same? M1 and M2 are matched with respect to each other. So do you see any symmetry between the two circuits? Yes, they are mirror images of each other. Both the sections and the left hand side and the right hand side are exactly similar. Even the power supplies are same. So here, if we make a cut in the middle like this, so we can say both the circuits are exactly symmetric. So we need not analyze entire circuit. We can analyze the half circuit. So this left half circuit and right half circuit are exactly same. So if you stand in front of a mirror, you see yourself, right? So this M1 part of the circuit, if it stands in front of the mirror, it will see M2 counterpart, which is the same. So we can say since both sections, including, I hope you're writing along with me, including M1 and M2 are symmetric, we consider only half circuit. So what do you mean by half circuit? Either you consider left half circuit or right half circuit. Are you getting it? Students, are you following what we are doing?
Yes, sir.
All right. You have to consider this. This is all under the assumption that your RD1 is equal to RD2. Your VTO1 is equal to VTO2. And your IDQ is equal to ISQ. That is what the assumption. So let's draw the half circuit. So here we are saying that it's symmetric. So we only consider the half circuit. So we only draw the half circuit and analyze. All right. So let's do that down. I hope you have completed up till here. I'm scrolling down now. Have you completed up till here? Yes or no? Hello.
1 second, sir.
Okay, complete it fast. So DC analysis is extremely important. And remember, for differential amplifier, there are high chances that questions will definitely come on differential amplifier. Either they will be in the form of DC analysis numerical or AC analysis numerical or the combination of both AC and DC. And then or it will be a derivation for ACM, for DC analysis or for AD, for any configuration. So there are high chances that there will be a question based on these topics, definitely with different, numericals with different, values. And theory wise, these are the things which we can be asked, which we are discussing today. So can I scroll down now? I am drawing now the half circuit.
Yes, sir.
This one. No need to draw the entire circuit. We just need a half circuit because the entire circuit is symmetric. So analysis with a half circuit will do. So let's draw the half circuit now based on this analysis. So write down half circuit. So what does this half circuit look like? You have a transistor M1. I'm drawing the left hand side of the circuit. Then you have gate terminal grounded. So now did you understand why doesn't the single input dual input matter? Because ultimately it's going to be, this is RD, this is supply, right? And here we have 2 RS. Yes or no? Now basically this is going to be plus VDD. Yes or no? And this is going to be minus VSS. So how do we connect them? We connect it like this. This is plus and this will be minus. Got it? And this will be grounded. Agree or no? This is VDD and this is minus. So automatically it become minus VSS. Automatically it will become minus VSS and this will become plus VDD. Agree to this? Here, let me add the currents now. So here, what is the current flowing through here? ID, Q. What is the voltage across this terminal? This is terminal, gate terminal and source terminal. So this is VGS. Okay. And what will be the amount of current flowing over here? ID again, because we are assuming IDQ is equal to ISQ. All right. So for the Q point means we need to determine the Q point. What do you mean by Q point? VGSQ and IDQ and also VDSQ and IDQ. So that is the expression which we want to determine. So all of you are ready? Can we start now? Acha, can you tell me why IG is 0? The gate current is 0. Why it is so? Is there any specific reason why the gate current is 0?
In MOSFETs, the gate current is zero, right?
Why it is so?
Because of the oxide layer.
Yes, because of the oxide layer insulating the gate from the source and the drain. That's why the gate current is 0. Now what we do is we apply KVL to gate source loop. So which is my gate source loop? Let me mark it with yellow color. This is my gate source loop. And it doesn't end over here. It ends when the ground is there. So it ends like this. So here we have to apply uh, KVL. So let's do that. We'll start from here, right? Ground, and then go to here. So here we're going from plus to minus. So it will be negative VGS, right? Minus VGS Q minus what will come over here? Twice RS IDQ, right? Twice RS IDQ. Now what will come over here? This is plus, this is minus, this is plus. So it is going minus plus VSS. So it will be what it will be over here? Plus VSS is equal to 0. Did you understand how did we apply KVL? Minus VGS minus IDQ twice RS plus VSS equal to 0. Why plus? Because we are going from minus to plus and the ground appears again. Did you all understand this? Yes or no? Hello. So what is VGSQ? It's VSS minus twice RS IDQ. So that's the expression for VGS Q. Acha, what is the expression for IDQ for a MOSFET in saturation? So we assume that both M1 and M2 are in saturation. So what will be IDQ given by? Kn times VGSQ minus VTO or VTN square. Correct? So that's the second expression. So please write down this expression number 1 and 2. From 1 and 2, you can determine what? Q point, VGSQ, IDQ. Okay? Understood this or no? Please complete it. I hope it is clear now. Everyone completed? Can I move on from this?
1 second, sir.
Remember, whether it will be any configuration, DIBO, DIUO, SIBO, SIUO, the analysis will remain the same, will not change. So in the exam, they can ask you, apply DC analysis and find the expression for VGSQ, IDQ and VDSQ. You need to do this analysis only. All right. Can I scroll down now? Have you understood it? Okay, fine. Now we go for KVL2. Now we are going to find VDSQ. Now we apply KVL2, the drain source loop. So let me quickly redraw the circuit for you all. This was grounded. And here I have two supplies. It's the same circuit. This is VDD. This was RD. This is twice RS. Now what is the drain source loop? That's the drain terminal. That's the source terminal. And this will be IDQ. This also will be IDQ. So where is the drain source terminal? Here. And where is my drain source voltage? Plus minus VDS. All right. Now let me mark the drain source terminal. Here it is. And this will be VSS. Now apply drain source, apply KVL to the drain source loop. So how do we start? Anyone? We'll start with VDD. We want to go like this, right? Let's go like this. Okay. So we are starting with VDD. So it's minus plus. So it will be plus VDD. What will come now next? IDQ into RD, right? IDQ into RD. Next, plus minus. So minus VDS. Then will come IDQ into twice RS. IDQ into twice RS. Then what will come? Then minus plus. So plus VSS, correct? So again, I repeat, we go in this direction. VDD minus plus, it should be plus VDD minus IDQ RD minus VDS minus IDQ into twice RS plus VSS is equal to 0, correct? So what is your VDS Q now? It's VDD plus VSS minus IDQ into RD plus twice RS. So this is the expression for VDQ. Please note it down. This expression number 3. So from here we can determine this Q point, VDSQ, comma IDQ. Understood this derivation? All right. Have you completed this? So let us summarize the DC analysis for a differential amplifier. It is valid for DIBO, DIUO, SIBO, SIU. So that's the good part of it. Okay. So what is the first formula? VGSQ is equal to VSS minus twice RS IDQ. That's the first formula. Second formula is IDQ. Remember, in this expression, VSS has to be considered positive, because already it's negative. So don't apply negative value again over here. It will be wrong. I hope you got it. IDQ is Kn times VGSQ minus VTO or VTN, whatever you call it, square. And what is VDSQ? It's VDD plus VSS into minus IDQ into RS plus twice RD. Okay, so these are the 3 equations from which you find the Q point. Either VGSQ, comma IDQ or VDSQ, comma IDQ. Understood? So this will summarize the DC analysis for this circuits. Completed, yes or no? Hello.
Yes.
All right. Now, you have written the formulas. Now, now I'll do something else. I'll give you the results for the AC analysis. We'll solve the numerical and then we'll come to the derivations. All right. So let us do that in the next 20 minutes. I hope you have completed it and you will summarize it and you will do it with proper care in exam if a numerical comes. Now let me give you a similar summary even before starting anything of all the formulas for AC analysis. So I'm not done AC analysis yet, but I'm giving the formulas for solving the numerical. So AC analysis, this is looking ahead. Okay. So for AC analysis, the formula for AD, write down the formula for AD, everyone. AD for DIBO is given by GMRD. Okay. ECM formula for DIBO is given by minus GMRD divided by 1 plus twice GMRS. We are going to derive all this, huh? Don't worry. In fact, in exam, they ask you the derivations only. You derived a differential gain. What is AD, by the way? Differential gain. What is ACM? Common mode gain. I hope it is clear. Okay. Sometimes they give, you use also this formula, ACM of DIBO. Sometimes it is also given by this RD upon twice RS. This is also the formula. All right. And then how do you calculate CMRR? CMRR basically in dB will be 20 log to the base 10 AD upon ACM. Don't take chances, just use this formula. CMRR will be 20 log to the base 10 AD upon ACM. So this is the summary of formulas for DIBO configuration. Okay. I'll give you the summary of formulas for DIUO configuration. So write down the formulas. AD of DIUO is actually half GM RD by 2. Okay. ACM formula remains the same. DIUO is minus GM RD 1 plus twice GM RS. It remains the same. So this formula also remains the same. ACM DIUO is given by RD upon twice RS. And again, CMRR is the generalized formula 20 log to the base 10 AD upon ACM. So what is the difference? This is by the way valid for SIBO also, and this is valid for SIU also. Okay. So all the four configurations have come: DIBO, SIBO, DIUO, SIUO. So fortunately, the ACM formula for all the configuration is same. Okay. The common mode gain formula is same for all the configuration. Only the differential gain formula for DIBO and DIO are different. So DIBO it is GMRD, DIUO is GMRD by 2. All right. Understood this? And by the way, how to calculate GM now? GM already you know. GM is given by delta ID upon delta VGS. You know the ID formula. Kn times VGS minus VTO the whole square. So you can differentiate this with respect to VGS and you will get GM as twice Kn VGS minus VTO. So note down the formula for GM also. So these are all the formulas for AC analysis. Okay, we have need to derive it. The derivations are long. So we will derive this formula, this one, this one, and this one. This will automatically come. CMRR formula will automatically come from AD and ACM. I hope it is making any sense. Please note down all these formulas. We are going to use that in the numerical now, which we are going to discuss next. And remember, it's a clue that AD will always be greater than 1 and ACM will always be less than 1. These are two golden rules. And CMRR will be always be greater than 1, of course. Have you completed this? Yes or no? Have you noted down? We are going to use these formulas by looking ahead. And then we are going to see the numeric, then we are going to see the derivations for it. Once we complete the derivations, that's it. The differential amplifier module is complete. Have you completed this, students? Yes or no? We are soon going
Yes.
to derive it. Yeah, we are soon going to derive it. Let me show it to you. See, in differential amplifier, we have completed so far terminology, quantitative description, DC transfer characteristics, then differential and common mode gain, CMRR. Okay. Then we have also completed DC analysis of differential amplifier. AC small signal analysis is left, which we are going to cover it today. And then tomorrow onwards, we'll start with current mirrors. Okay. So let's start with the numerical. Very, very important. I'm only going to solve only one, and rest will be the variations of it. All right. So
Sir, could
numerical
you
number.
send Sir, could you send the recording of the last online class that you took?
Yeah, yeah, definitely. I'll send it by today. Everything.
Thanks.
Yeah. So write down find IS, ID1, ID2, VGS1, VGS2 for V1 equal to V2 equal to 0. B part, find differential gain, VO2 upon VD. Find common mode gain, VO2 upon VCM. And third thing, find CMRR in dB. And the transistor parameters are, we can write over here, transistor parameters. Basically, they're asking us to find the Q point. Transistor parameters are Kn1 is equal to Kn2 is equal to 50 microampere per volt square. And VTO1 is equal to, sometimes they call it VTN also. So it's one and the same, is 1 volt. And now let me draw the configuration. So this is the configuration in front of you. Okay, it's a dual input, but an unbalanced output. This is RD1, this is RD2. This will be RS given to you directly actually. How much it is? 20K. This is minus VSS, which is given as minus 5. Let me write the values now. This is 20K. This will be 25K. This will be 25K. This is M1, M2. This is V1, V2, plus minus, plus minus. And output is taken from this terminal. So output is with respect to ground. Okay. So this is VO2, or we can write it V out, also called as VO2, because it's taken across this second transistor terminal, drain terminal. Completed? Acha, how to identify the configuration? That's the first thing which you do. See, both the inputs are there, so it's a dual input. Balance output will be when both the outputs are also there across both the drain terminals. But here it is only one terminal. So this configuration is dual input, unbalanced output. Okay. It doesn't matter to DC analysis, but it will matter to AC analysis. So it's a dual input, unbalanced output. That is DIUO, DFAM, differential amplifier. Completed. Have you completed writing the numerical? Yes or no?
Yes.
Numerical wise, it's very easy. First, identify the configuration. If there was two outputs connected, it would have been DIBO. If single input was connected, would have been SIUO or SIBO, depending upon where the output is connected. If output is measured with respect to ground, it's a UO, unbalanced output. If they are measured with respect to each other, then it's a BO, that is balanced output. So let us start with the solution. Okay, this is plus 5. VDD is plus 5. VSS is minus phi. Now it's important to draw that half circuit also for DC analysis, remember? So first we'll go for DC analysis. Okay. So what was the DC analysis? We consider only the half circuit. So this is my half circuit, correct? This was grounded. This was VDD, VSS, RS. Actually, it is twice RS, no? Do you agree? Because you split it into two parts. Yes or no? Twice RS, then it will be RD, and this will be connected to the ground. I hope it is clear now. This is M1 transistor. This is current IDQ, and this also same current IDQ. Just for the formality, we have done it because we already know the formulas now. If you wish to apply again, you can apply this analysis again, or else you can directly use the formula, but not without drawing the circuit. You have to draw the circuit this way. So we consider half circuit because it is symmetry, right? Due to symmetry. Okay. So what is the formula for VGS Q1? Because it is transistor M1, right? Just now we have written just 5 minutes back. I'm not going to solve it again. It's VSS minus twice IDQ1. I'm writing 1 because it's for transistor 1 RS. Okay. Yes or no? That's the formula we have now. So VGS1 will be equal to what is VSS phi. Don't substitute it as minus phi. That's what I'm saying because already it's considered negative sign. So it's phi minus twice. How much is RS? 20K. So it will be phi minus 2 into 20 into 10 raised to 3 times IDQ1. This is equation number 1. Got it? Then we will write assume both transistors are in saturation. Assume both M1 and M2 are in saturation region of operation. So therefore we can write IDQ1. Why we are 1 we are writing? Because it's for transistor 1 is KN1 into VGSQ1 minus VTO1 square. Okay. We are writing deliberately 1 because it's the same thing only. You are with me? So IDQ1 will be equal to 50. Now it is KN1 is 50 micro. See, it is 50 microampere. So it will be 50 into 10 raised to minus 6 into VGSQ1. VTON is 1. So it is like this. So this is our equation number 2. So have you written equation number 1 and 2? So this is basically DC equivalent half circuit due to symmetry of both sections. We can add a point over here. Completed up till equation number 1 and 2. Sorry for this. Yes or no? Now equation
Yes.
number 1 and 2, there are two unknowns, VGS and ID. So and there are two equations. So what you will substitute where? So put equation number 2 in 1. So write down substitute equation number 2 in 1. Always, huh? So we can write this VGS1 is equal to phi minus 2 into 20 into 10 is to 3 into IDQ. IDQ is this 50 into 10 is to minus 6 into VGS cube 1 minus 1 the whole square. Correct? That is what we have written over here. So how much is this? Calculate it. I think this will be 2 only. Just check, cross check. 20 kilo into 50 micro will be around 1. Is it? So VGSQ square minus twice VGSQ1 plus 1 like
Yes, sir,
this.
it's 2.
Yeah. Now it's just a matter of quadratic equations and all. So twice VGSQ1, I'm skipping one step over here, minus 3 VGSQ1 minus 3 is equal to 0. You can cross check it. Now solve this quadratic. You will get 2 equations of VGSQ1, out of which only one will be correct. So tell me these two values. Yes, what are its values? Solve it by quadratic equation. How much is VGSQ1? Yes, tell me. How much it is?
So 2.186.
Yes, correct. And minus 0.6.
0.68. 6.
686. Yeah. So which one will you select and which one will you reject?
Select 2.186.
Why? Because VGSQ should be greater than VTO, which is 1 volt. And this you reject and this you accept. Okay. So what's the final answer of VGSQ? 1, which is equal to VGSQ2, right? Because it's a symmetric circuit. It's 2.186 volt. And now we find the value of IDQ1, which is KN1 into VGSQ1 minus VTO1 the whole square, which will be 50 micro into 2.186 minus 1 the whole square. Let me know how much is the value of IDQ. IDQ1 is how much? Yeah,
7.7 micro ampere.
it's 70.33 microamperes, correct? Or it
Yeah.
is rather 70.33 into 10 is to minus 6 amperes, which is nothing but, if you don't want to write this microampere, then let it be this only, but don't write it wrong. So it's microamperes, correct? And now due to symmetry, we can say IDQ1 is equal to IDQ2 is equal to 70.33 microamperes. Got it? So here it is. We are supposed to find VGSQ, VGS2 for V1, V2 equal to 0. That means for DC analysis. We also need to find IS. Now, how to find IS in this expression, in this diagram? See, basically IS is basically ID1 plus ID2, correct? IS is given by ID1 plus ID2. So we have to just add the two currents. So write down next IS will be given by twice ID, or we can say ID1 plus ID2. If both are same, it will become twice ID, correct? Because ID1 is equal to ID2 is equal to ID. And how much is that? Twice into 70.33 microampere. So how much it is? 118.6. Oh, sorry, 140 point. 66 microampere, is it? Yes or no? Correct? Hello. Are you all getting such answers? IS is this much, 140.66 is a double of IDQ1. Yes or no? Now next step will be finding the small signal parameter GM. What is the formula for GM? Twice Kn VGS minus VTO. Now I'm not writing any numbers because this GM1, let's say if I write this numbers then. Okay, remember there is no square. So twice into 50 micro into VGS1, which is 2.186 minus 1. So calculate GM1 for me. And then we say GM1 is equal to GM2 is equal to GM. How much it is? 100 micro into 2.11186 minus 1. Yeah, let me know the value.
1.186 into 10 to the power minus 4.
0.11 milliampere per volt. Correct?
Yes.
So that's the value of GM1 equal to GM2 equal to this much, 0.118. Or we can write 118 microampere per volt. So it is 0.118 milliampere per volt. So that is the answer. Now we go to third part. Now which configuration it is? DIUO, DFAM. Yes or no? So which formula do we use of AD? So what is AD of DIUO given by GMRD by 2, correct? So GM is how much? 0.118 into 10 raised to minus 3. RD is how much in the numerical? 25K. So 25 into 10 raised to 3 divided by 2. So this 10 raised to minus 3 and plus 3 will get cancelled. So let me know quickly how much is this answer? What is differential gain of DIUO? Is it 1.4825? Quickly tell. Is it? Differential gain is 1.4825. Can anyone confirm?
1.475.
475. Okay, you have substituted 0.118. Acha. That's okay.
Yeah.
1.48, 1.47, it's fine. So 1.48, that's important. Remember, AD is greater than 1. Now we'll calculate ACM. So what is the ACM formula? Mod of for DIUO. It's the same for all actually. GMRD divided by 1 plus twice GMRS. So please calculate this. GM is 0.118 into 10 raised to minus 3 into RD. RD is 25 into 10 raised to 3 divided by 1 plus twice GM 0.118 into 10 raised to minus 3 into what is RS? RS is 20K. Substitute over here. All right, now calculate this and let me know the answer. Remember, it will be less than 1. ACM, I can confidently say it will be always be less than 1. How much it is? Yes, students. What's the answer? Final answer. Let me know. Sorry,
So zero. Uh, I get something wrong.
0.51.
515. Yeah.
Yeah, that's correct. Now remember, we have used the approximate formula also. This is the exact formula. What was the approximate formula? Mod of RD upon twice RS. Yes or no? Have we done this or no? ECM we have written now. Yeah, RD upon twice RS. So by this formula, what's the value? It's 25K divided by 2 into 40, 40K. Is this coming same? This was approximate formula. Just cross check this also. What is 25 upon 40? How much it is? This is
Zero
5,
point 625.
0.625.
625.
So always use the exact formula, not this. This will be erroneous. This is approximate result, which is not always correct. So always use this exact formula. Now next we have to calculate CMRR. Remember, this is very important numerical going on. High chances are that this will come with different values in exam. So don't skip this. Either this or the derivations or the DC transfer characteristics or the functionality of the differential amplifier. So this is AD upon ACM. That will be 1.48 divided by 0.515. How much is this? Is it 2.8 something? Just check. Hello. Is this the value?
Yes, sir. 2.873.
Now, this is not the end. Last CMRR in dB will be 20 log to the base 10 AD upon ACM. So what you need to do is 20 log to the base 10 of 2.8. 2.8 what? Is there any digits ahead? 2.8. Tell me.
737.
So now tell me the value exact in dB. So it's do 20 log to the base 10 of 2.873. That will give you the final answer. And this will fetch you very important 10 marks. It's a 10-mark question. In a 50 marks paper, 10 marks are extremely important. Okay. How much is the value? Is it 9 point something?
Yes, sir. 9.166.
Yeah, that's the answer. So yeah, this is it. I'll give you the marks distribution for it because that is important that you should know. Okay. DC analysis will fetch 5 marks. So up till here, you will get 5 marks. Okay. And AC analysis will fetch you another 5 marks. So up till here, you'll get 5 marks. So therefore 10 marks. Okay. So if DC analysis is wrong, everything else will be wrong. So practice this numerical, and I've already shared you the previous module questions. Okay. Let me show it to you. Uh, Let me so exam questions from module number 5. You can have a look at it. There's a previous questions, right? So this is one of them. Okay. This is the second one. This is the same numerical which we have solved. Then there are this some numerical. As you can see, number of time the question is asked. This is a derivation. Okay. So high chances are now the numerical will come definitely. And these type of questions can also come. All right. Okay, this type of questions can also come. See this question number 7. We'll solve it here only. Calculate the value of CMRR in dB for a differential amplifier. Differential voltage gain is 100. So AD is given as 100. Common mode voltage gain is 0.02. Calculate CMRR in dB. So simple it is. But first of all, CMRR will be AD upon ACM. it will be 100 upon 0.02. Very simple, right? Yes or no? So this you can solve it easily. CMRR in dB will be 20 log to the base 10 AD upon ACM. So such simple questions are also sometimes asked in the exam. Okay. So please solve further questions from it. All right. Everyone comfortable with numerical number one? You have any doubts, you can ask right now. But practice just numericals with different values in exam. Yeah, students. Can we go for the derivation or you want me to wait?
You can go to the derivation, sir.
All right. I'll start with the derivation for the differential amplifier, small signal or AC
Sir,
analysis.
just a second. I'll just. Okay. Yeah. Sorry.
Okay, I'll wait. So there are, let me talk during that time. There are three possible questions which can be asked in exam. First will be the functional question, the functionality question. What is a differential amplifier? What are the different types? Explain the working of differential amplifier with the help of DC transfer characteristics. The second question will be derive derive and draw the DC transfer characteristics for a MOSFET amplifier, MOSFET differential amplifier, sorry. The third theory question will be derive the expressions for the DC Q point in a MOSFET differential amplifier, or derive the expression for differential voltage gain, common mode voltage gain, or CMRR for a differential amplifier for any configuration, for DIBO or DIUO. Okay. Derivation for DIUO and SIUO will be same. Derivation for DIBO and SIBO will be same. Then very important, they can ask you a full-fledged numerical on differential amplifier as we have solved just now. I hope it is completed, everyone.
Yes,
Please,
sir.
please do practice this because only in the
Sir,
exam. Yeah,
is it necessary to write it in decibels at the end as the final answer?
of course, yes. I'll have told you this. I'll tell you again. If the answer is between 1 and 10, you have to write up till 4 decimals after point. Okay. If the value is from 10 to 100, you have to write up till 2 decimals. If the value is 100 to 1000, you can write up to 1 decimals, and beyond 1000, no need to write. You can approximate it after decimals. Understood this? If the value is after between 1 to 10, up till 4 decimals, and beyond, if it is below 1, then up till 5 decimals. That's the general rule of trend. Okay. So please see what can be different in this numerical. Sometimes in exam only one input will be given. What difference does it make? Okay. Sometimes both the outputs are mentioned over here. That will be balanced output. In that case, the DC analysis will remain same. In AC analysis, what will change? This GMRD by 2 will become GMRD. That's it. Everything else will be same only. Correct? Only this gain will be double. ACM value will remain same and CMRR will also be remaining same. So please practice this numerical. Okay. Now for home assignment, what you can do is take the home assignment. Take this numerical for home assignment. So find AD, ACM and CMRR. The value of K is uh, 0.5 milliampere per volt. Okay. VTN, actually KN1 equal to KN2. VTN1 equal to VTN2 is equal to 0.8 volts. This is the configuration given to you. This is plus 5 volt. This is RD. This is 33K. Okay. and output is taken across both. So this is a balanced output, as you can guess. All right. So resistance will come over here and it's connected to a negative supply. Its value will be 24K and this is minus 5. Here input is connected to AC input plus minus V1 plus minus V2. All right. So first of all, do you identify the configuration over here? Which configuration it is? Dual input. Which is it? There are two inputs and two balance output, right? So it's a DIBO.
Balance, yes.
So solve it when you have time and get the answers. I don't have the answers because I've just created this just now. So that's the way we can change. Okay. This is RS. All right. Now can we go for the derivations? Yes or no? Yeah. Let's go for the derivations now. Write down AD, ACM and CMRR. Derivation for DIBO, DFAM, differential amplifier, or it is simply called as AC analysis. Okay. Now for this, we'll use the same diagram as we have used over here. So let me draw it over here. There's a reason I'm drawing very tiny. You'll understand very soon why. Please draw this. This will be plus VC, VDD. And it is DIBO, so plus minus V out. Okay. Let me complete it. This is V1. V1 and V2 are AC signals. Huh? Remember that. This is M1, M2. This is RD1. This is RD2. Remember they are symmetric. Huh? So even though we are writing RD1 and RD2, they are same. Okay. So that's your DIBO configuration. DIBO DFAM. This we have already know. Now we go for AC analysis. All of you ready? This much you two you don't know, right? Hello. Yes or no? Can we start with AC analysis? Everyone? You all are with me? Can we start? So for AC analysis, we remove all DC sources. So what do? We make VDD equal to VSS equal to 0, short circuited. Okay. And in the next step, we replace M1 and M2 with its small signal model. We replace M1 and M2 with its small signal model. Okay. What is a small signal model for a MOSFET? I hope you have started studying it. So that's my gate terminal, drain terminal, source terminal. So between the gate and source, it's open circuit VGS. Between the drain and source, what it is? GM-VGS. We assume that RO is infinite over here. So does this small signal model will replace this? Okay. We'll replace this MOSFETs with the small signal model like this. Can we start? I mean, can I start directly? Hello?
Yes, sir.
Okay. So first of all, I'll draw on the right hand side only. You will understand and appreciate why I've drawn so small now. Because I want to fit everything in one screen. Now I'm only drawing the small signal model for M1. Okay. So for M1, here it is. So this will be, okay. Before that, I'll mark over here certain things. This is gate number 1 because it is transistor 1, right? This is gate 1. This is drain 1. This is source 1. This will be gate 1. Sorry, gate 2, drain 2, source 2. Correct? Just for the notations for M1 and M2. Now we are drawing the small signal model for M1. So this will be gate 1, drain 1, and source 1. So what is bit connected between gate and source? Open circuit. Just VGS1. Correct? What is connected between drain and source? Come on, just now we have drawn now a voltage dependent current source. GM1, VGS1. We'll stick with the notation. Actually, GM is same. So we'll write GM only. GM1. No, GM only. Okay. And the top of it, here it is drain 1 terminal, right? So we have drawn this. Okay. Now from the drain 1, what happens? Drain 1, it's connected to RD1 and that is connected to ground because VDD has to be sorted. So here I'll connect one resistor RD. RD1 and RD2 are same and that will go to the ground. What is there on the drain 1? Out VO2, VO1. This is VO1, this is VO2. So this I'm calling it as VO1. Okay. From the source side, we have a resistor. So we have a resistor RS connected over here. So this resistor is, I'm connecting it over here. Is it goes to the ground? Yes, because VSS will be sorted. So this will go to the ground. This is RS. And what happens at the gate terminal? At the gate terminal, you have your signal source. This is plus minus V1, which is AC signal. Got it? Yes or no?
Yes, sir.
One half of the circuit completed. Now the mirror image, huh? See how it is connected. The gate terminal is connected this side. Okay. So we will also draw it this side. Gate 2. Here we will draw drain 2. No problem, right? This is source 2. Okay. What is connected between gate and source? VGS 2. What is connected between drain and source? GM into VGS 2. Correct? And what is connected between the gate terminal? Your source. Plus minus V2. See over here. Between the drain 2 terminal and ground, we have RD2, which is RD only over here. Here it is. RD. And the drain terminal, we have connected VO2. So here it will be VO2. And from the source to terminal, it will go to a resistor wire to ground. So this will go to resistor via ground like this. It is going like this. Correct? So this is my small signal equivalent circuit. Write down small signal equivalent circuit for DIBO differential amplifier. Please draw the circuit now. My entire derivation lies with drawing this circuitry perfectly. Actually, to make it symmetric, I'll show it from here. This looks symmetric. I hope it is clear. We have replaced DC sources VDD and VSS by ground. And we have replaced M1 and M2 with a small signal model, which is over here. We have assumed RD is infinite. Okay. So we have the following assumptions also. Here we have assumed, and let me write it down. RD1 is equal to RD2 is equal to RD, and both the transistors are matched. So GM is equal to GM1 is equal to GM2. Okay. And V1 and V2 are differential. Okay. That's what we are analyzing for. For differential means they are different, either in magnitude or in phase. Have you completed this circuitry? Yes or no? Doing it still? Okay, do it. I hope it is clear. So basically we can say GM1 is equal to GM2 is equal to GM. That means both the transistors are biased at the same Q point current and hence the GM are same. Remember, for differential mode operation, inputs are equal in magnitude but opposite in phase. So basically when we say V1 and V2 are differential, what we mean is V1 is equal to minus of V2. Okay. So both are same in magnitude but difference in phase. That is what we mean. Got it? Hello. Completed this or no? Can we start with this derivation? At least we'll complete DIBO today. Then
Yes.
DIUO we can do it tomorrow. So that means that, let me show it to you. Differential means this. So we have considered input and like this. And here it will be like this. Out of phase. Same magnitude but out of phase. So basically V1 will be equal to minus of V2. This is AC signal. Right. Now, can we start? Now tell me, step number one, how much is VGS1? Can I say VGS1 is VG1 minus VS1? Agree? Which is equal to VG1 minus VS, because this voltage is same. This voltage is VS. VS1 is equal to VS2. Huh? Similarly, VGS2 is equal to VG2 minus VS2, which is VG2 minus VS. VS is common. Correct? That's the first step. Second step is we apply the KCL at node VS, at this node. Okay. Now you need to tell me which are the currents flowing. Here. Tell me which is the current flowing over here. First current flowing is this current source, right? Which is nothing but GM into VGS1. Correct? Second current is this current, which is GM into VGS2. Third current is this current. Can you tell me how much is this current? Please, can you tell me how much is this current? This is a resistor. This is a AC voltage Vs. So what will be this current? Vs upon Rs. Agree or no?
Yes.
Okay. So what is my KCL at node VL? So write down second step. KCL at node Vs. What do we have? Two incoming currents are there. GM into VGS1 plus GM into VGS2 is equal to Vs upon Rs. Incoming currents are these two and outgoing current is VSRS. So that is GM into VGS1 plus GM into VGS2 is equal to Vs upon Rs. Let's call this equation number one. Correct? Now, GMB take it here common. We get VGS1 minus VGS2 is equal to Vs upon Rs. You're writing along with me? Now, what is VGS1 minus VGS2? From here, from 1, we can say it is VG1 minus Vs minus of VG2 minus Vs. Yes or no? What gets cancelled? Vs, right? It is VG1 minus VG2. Yes or no? And what is VG1 actually? Gate voltage is nothing but V1 now. So VG1 is actually V1 and VG2 is actually V2, correct? So we can say VG1 is actually V1 and VG2 is actually V2. Yes or no? So we can write it's V1 minus V2. So we can rewrite this equation now. That is GM is, no, it will not cancel out. It will become, how much it will become? Plus now. Oh, it is plus, not minus. Oh, sorry, my bad. It is plus. Okay, so what it will become? V1 plus V2 minus twice Vs. Yes or no? Hello, are you listening? See, VG1 is V1, VG2 is V2, and this will be minus Vs, right? So VG1 is V1, VG2 is V2. Are you agreeing to this? So now VGS1 plus VGS2, this is plus, huh? Yeah. So how much is this now? V1 plus V2 minus twice Vs is equal to Vs upon Rs. Agree to this? So I can say Gm into V1 plus V2 and Vs we can do it over here. So we can Vs common, what do we get? 1 upon Rs plus twice Gm. So how much is Vs now? It's V1 plus V2 upon, we can take Gm inside and what do we get? So what is this step? V1 plus V2 is equal to Vs times Gm, we take it down. So what do we get? 1 upon GMRS plus 2. Yes or no? Students, you all are present. Please respond yes or no. This is equation number
Yes.
2.
Yes.
Actually, this equation number 2 will be useful in ACM derivation, but still, we are almost coming to the end of the derivation for AD. How much ever we complete till 8 p.m. we will complete now and then we'll do it tomorrow. Up till here completed? So you all are just listening or writing, I don't know. So now
Yes,
step
sir.
number 3. Yeah, step number 3. Now, write down, since it's a DIBO DFAM, we can say output is equal to, now let's go to the diagram. Output is plus minus over here, P out. Yes or no? Mark it in the in your this thing. It is plus minus over here. So it is V out is VO1 minus VO2. Agree? V out is VO1 minus VO2. So that's what we write over here. V out is VO1 minus VO or VO2 minus VO1. Actually, we can do it the other way around also. Whatever the case. If we do VO1 minus VO2, it might come negative, but that's okay. So it's VO1 minus VO2. Okay. Now, from this diagram, can you tell me what is VO1? Can you smartly tell me what is VO1? Do you know over here, same current flows through this resistor also, right? And how much is this current? This is a current source, right? Current is how much? GM into VGS1. So how much is VO1? Voltage VO1 is this current into this resistance. But this current is not entering the ground. It is leaving the, I mean, not leaving the ground actually. It's actually going in the opposite direction. So the voltage will be negative. So what I mean to say is V is equal to IR. VO1 will be minus of GM VGS1 into RD. Did you get it? Why minus? Because if it was entering the ground, then it would have been plus. Now it is going away from the ground. Hence it is negative. Do you agree or no? This thing. Yes or no?
Yes.
Similarly, VO2 will be minus GM VGS2 into RD. So let me write it over here. Now, VO1 will be minus GM into VGS1 into RD. Acha, what is VGS1? VG1 minus VS, right? Or we can write V1 minus VS. So VGS1 is VG1 minus VS, that is V1 minus VS. So we can write minus of GM into RD into V1 minus Vs. This is VO1. Let's call this equation number 3. Okay. Similarly, VO2 will be minus GM times VGS2 into RD. So what is VGS2? VG2 minus Vs, that will be V2 minus Vs. So it will be minus of GMRD into V2 minus Vs. Agree? Equation number 4. Yes or no? Now we write output V out is equal to VO1 minus VO2. So what do we get? Minus GMRD will be common because it is common. And inside the bracket, what do we get? V1 minus Vs minus of V2 minus Vs. What gets cancelled now? Vs gets cancelled. Yes or no? And how much is the output? So output is minus GM into RD into V1 minus V2. Agree? Yes or no? This is equation number 5. Now what is differential mode input signal VD given by V1 minus V2? Yes or no? We have said now V1 is equal to minus V2. So here VD differential mode signal is V1 minus V2. And what is my output? What is my AD given by basically? V out upon VD, where V out is VO1 minus VO2 upon V1 minus V2. Now tell me what it is. AD now minus GMRD. Yes or no? Because here, if I V out, this is nothing but VO1 minus VO2. Okay, divided by this. So that will be minus GMRD. Okay, and that's the derivation for DIPO. Now you will say, sir, why I've written plus? It's always considered to be magnitude. So it's AD DIBO will be mod of GM. What does the negative sign indicate? That input and output are out of phase with each other. That's it. Correct. So that's the derivation for differential mode gain. This is differential mode gain. Understood this? Yes or no? Hello,
Yes.
students. Have you? This was the step we have arrived, right? Earlier also we have solved a numerical and we have arrived at this step. Now let me also complete common mode derivation and then we will end for today's lecture. Can we start for the common mode operation? Hello students, yes or no?
Yes.
Okay, so write down ACM derivation. Okay, for ACM derivation, there are two conditions. First of all, we select both inputs to be equal in magnitude and phase. That's the definition of common mode signal. Equal in magnitude and phase. That is, V1 will be equal to V2 will be equal to V. So if we do that, let me quickly draw. You don't draw the equivalent circuit. I mean, it will be advisable if you just pay attention to this derivation. Instead of writing, you can write it later. So it will be VGS 1. And here also, let me complete it fast. GM into VGS 2. Then this will be G2 plus minus VGS 2 plus minus VGS 1. Okay. Here there was a resistor RD going to the ground. Here there was a resistor. Okay. A resistor RD. And output was taken across this VO1. And here it is VO2. All right. Okay. Just wait a second. Yeah. Now, see one thing over here. What is so special about common mode signal? In a common mode signal, V1 and V2 are same. So that means here I'll write it as V. This is equal to V. This also equal to V. Yes or no? Agree to this? Hello. Yes or no?
Yes.
Normally this would have been drawn like this. And this was grounded, RS, right? But what we do is this RS can be drawn as equivalent of 2 RS. Correct now? A single resistor RS can be written as 2 RS parallel to 2 RS. That will be RS itself. There is a reason why we are doing it. So we combine this and we drop it down into two parts. 2 RS. There is a reason why we are doing it. Just wait. And we chop it down over here. Okay. Now, if you see carefully, what is VGS1 equal to? VGS1 will be equal to V1 minus VS, right? This is VS, right? V1 is same as V. And what is VGS2 equal to? VG2 minus VS, right? VG2 is equal to V. So both mean same. Both are same actually. So here now the circuit is exactly symmetrical. Mirror image of each other. Yes or no? So here, since the circuit is exactly symmetrical, we can cut in half like this. If we cut in half, it will be the mirror image of each other. So that's the sectional cut. All the elements are same. Even VGS1 is equal to VGS2. Nothing is different at all. Okay. How can we do it? See, since V1 is equal to V2, this will make the AC equivalent circuit exactly mirror images of each other. So both sections are mirror images of each other. Yes or no? So both sections including M1 and M2 are symmetric. So we'll analyze only one half of the section. Okay. We'll analyze only one half of the section. Do you agree on this? Both are exactly the same because V1 and V2 is also same. So VGS1 will be equal to VGS2 will be equal to VGS here in this case, especially not in case of differential input. Okay. Can we analyze the half circuit now? Quickly, can we do that?
Yes, sir.
Okay. So I'm redrawing the same circuit again down. So let's analyze this half circuit. Let me highlight this part. Let us analyze only this much circuit. So this is my half circuit. Okay. Yes. So I'm not drawing it separately. I'm doing it here directly over here right now. All right. Now, can I apply KVL over here in this loop? In this loop, I can apply KVL. Yeah, like this. Okay. So what I will do is I'll apply the KVL to loop number one, this loop. This is my loop one. What do I get? This is V, huh? This is V minus plus, it's rising. Then fall in potential minus VGS, not VGS1, huh? Then minus, this is what is the current flowing to this ID, right? So minus twice ID RS is equal to, no, not ID, sorry, not ID. What will be it? We are analyzing this part of the circuit, no? So what is the current over here? GM into VGS, right? So twice GM into VGS into RS. Agree? Twice RS into this current now, which is flowing over here. So current flowing over here will be how much? GM into VGS. Why? Because VGS1 is equal to VGS2 equal to VGS. So what do we get over here? V is equal to VGS plus twice GM VGS RS. Okay. So V will be equal to VGS common 1 plus twice GM RS. This we call it equation number A. Do you agree on this? Hello. Yes or no? This is V minus VGS minus twice RS into GM VGS. So we got equation number A. Is it not? Now tell me from here, what is VO1? Minus, this is what? GM VGS, right? So it will be minus GM VGS into RD. Similar to last time we have done, right? But in this case, it is VGS, not VGS1. Correct? This is the current. Why minus? Because it is leaving, because it is moving away from the ground. So that's why the current direction will be minus. So minus GM into VGS into RD. So what is VO1 now? Minus GM VGS RD. This is our equation number B. Okay, fine. We have VO1 and we have V, total V. Acha, tell me what is the common mode input given by VCM? It's V1 plus V2 divided by 2. What is V? V1 V. What is V2 V? By 2. It is how much? V only. So VCM voltage is V alone. So what will be ACM now? It's output V out upon VCM. Yes or no? So now VO2 will be also same, right? VO2 will be what? VO2 will be minus GM VGS into RO. It's one and the same only, right? So GM VGS RD. So VO1 and VO2 are same. That's why we consider only V out directly. Okay. So how much is V out now? Minus GM VGS into RD. And what is VCM? It's V, right? What is V from equation number A? It's VGS into 1 plus twice GM RS. What gets cancelled out over here? VGS gets cancelled out. So ACM will be how much? Minus GM RD divided by 1 plus twice GM RS. Okay. And that is the derivation for ACM. Understood this derivation? So in this derivation, you might be confused why V out is this only. See, in this case, V out is either VO1 or VO2, not VO1 minus VO2. Huh? If you do VO2 minus VO1, it will be zero because both are same. So either VO1 or VO2. In this case, in common mode signal. Okay. So hence this derivation, ACM for DI-BO is this much, which we have already derived. Yes or no?
Yes, sir.
And how we can approximate it? We can, if we approximate 1 plus twice GMRS as approximately equal to twice GMRS. So what do we get? ACM is minus GMRD upon twice GMRS. So that's why we get this formula RD upon twice RS. All right. Now, if someone wants to calculate CMRR ka formula, then how we can calculate if they want to derive it? So CMRR is AD upon ACM. What is AD given by? GMRD. And what is ACM given by? RD upon twice RS. Let's say use this approximate formula. So what do we get? Actually, it's not this one, it is mod. What do we get? Twice GMRS. So CMRR, if you want to write for DIBO, is given by this formula. It's approximately given by twice GMRS. So if you want to improve or increase the value of CMRR, how can we do it? What are the ways? Either increase GM or increase RS. Yes or no? And that's what we'll do next time. The value of CMRR will be increased by increasing the value of source resistance. GM we can increase, but that will disturb the Q point of the system because GM is dependent upon ID and ID is dependent upon VGS. So entire Q point will get disturbed. Okay. So it's a mandatory, it's a good strategy to increase GM by increasing the value of RS by increase GMRR, CMRR by increasing the value of RS. By the way, what was CMRR full form? Common mode rejection ratio. Okay, fine, understood. So that completes the derivation for AD, ACM and CMRR for DIBO. It's also for SIBO. It's the same thing. No difference at all. Okay. Now next time, that is tomorrow, we'll do the derivation for DIUO. Which derivations? AD, ACM they're same and CMRR. Okay. So that's it for today. Thank you all for joining. If you have any questions, you can ask. Do you have any questions?